Hey everyone, welcome back. In today's video, we're going to be starting a new topic. That topic is velocity. Before we begin, let me say though that this is one of the most important topics that we're going to cover in dynamics. It is imperative that you know how to take derivatives to find velocity. If you can find velocity, it is just repeating that same process to find acceleration. And you are going to have to do this all semester long. So make sure you feel comfortable with it. Recall from previous discussions, previous topic, we covered both position and orientation. And this is how we define the instantaneous state of your body. So for example, here's the body. Position is just where it is, and then the orientation is, of course, how it has been rotated. This was P, and this was R. Now, what we're going to do for velocity is each of these, position and orientation, are going to have their own velocity. So, position is going to give rise to linear velocity. And the symbol for this one is going to be V. And then the orientation, this will give rise to angular velocity. And the symbol for this one is the lowercase Greek letter omega. So it's going to look like W's. When you're working a problem, suppose I give you 4-bar linkage, which we've seen several times now. Here it is. And attached to this coupler could have some kind of unique geometry, and attached to this coupler is some other point of interest, D. Let's say point D. And I ask you questions about point D. I could say, give me a position vector to point D. Give me the orientation, right, to find the rotation of this coupler, body B. Next thing I could ask is I could ask for the velocity of point D. I could ask for the angular velocity of body B, things like that. The process for finding that, you still need to do position, you need to do orientation, you need to do constraints and degrees of freedom. And then, once you have answered these parts, then we're going to go through, and I usually recommend defining angular velocity first, because it ends up actually being really simple, and then linear velocity next. Okay, so we're seeing this pattern develop, and this is going to be our recipe for the semester. If you follow these steps, you'll be able to do the dynamics for any problem. All right, so we want to, we're going to do several examples where we call out these quantities, and this is going to be the start of a whole series of videos talking about velocity and its applications. So, as we did with position orientation, we need to work a couple of different examples. We're going to do 3. We're going to do the sliding block that only translates, the spinning pendulum that only rotates, and then we're going to do the block in the groove of the pendulum so that we can see objects that rotate and translate. So let me clean this up and let's get started. Let's start by looking at the sliding block. We know how to set this problem up. I will put some inertial point in. I will put another point, we could say at the block center of mass, point A. We know we need some non-moving inertial frame. I'm just going to call that N frame. On exams, on homework, please distinguish X and Y. And then we need some A frame, so XA and YA. We know that we have to do position vectors. There is some translation variable here, Q. So this is Q in the X hat N. And we know that we would define the rotation. In this case, the rotation is very simple. It's not moving. There is no rotation. So YA is YN, ZA, ZN. And do some little diagram that goes with it. Okay, so all of this has been covered in previous videos. I expect you feel comfortable with it by now. What do we need to do next? Well, formally, we need to list generalized coordinates and constraints. We look at this whole write-up. Notice there's no angle of rotation. The only thing in this problem is a translation. There is only one generalized coordinate, and that is Q. There are no constraints on this problem, and there is one degree of freedom. So that Q is independent, right? You can grab the block and you can slide it back and forth left and right. Now, some other comments on this no constraints. Consider that in reality, if this was our block, it can slide left and right. It can also slide in and out, and I can pick the thing up and bring it down. So depending on the complexity of the problem, you may have additional coordinates and you may have to go back and revise this no constraints. All right. The fact also that we define that there is no rotation means that this block isn't ever going to tip. We haven't added any tipping into the definition of the problem. If we were perhaps applying forces, which we will do later, if we were applying forces at the top corner that may cause this thing to tilt, then we would have to define some rotation in the system. Okay, so we have the write-up for this problem. You have it all in your notes. We want to discuss the velocity of this problem. And remember, we have two types, angular and linear. My advice is to actually do angular first. Most problems, especially problems where you're doing simple rotations, right? The angular velocity you can usually just write down from observation. Just look at this thing and you can tell how it's rotating. In this problem, it's not rotating. So what do we need to do? What I want you to do is I want you to write omega, and this is omega in to A. The letters on omega correspond to the letters on the rotation. You define the rotation for this problem from in to A, so we're looking at the angular velocity into A. Another way to say it is the angular velocity of the A frame with respect to the N frame. So what is the angular velocity of this? Well, A frame doesn't rotate, so there is no angular velocity. I need you to write this down on your problems. You have to communicate with me in the grader that you know what's going on. So please include that. If you don't, then I don't know that you know that. Next, and of course we're going to get to more complicated ones in a bit where it's not zero. So really for this one we just have to do linear velocity. Okay, the symbol for linear velocity is going to be a V, and we are going to put some letters on this. So I'm going to save a little space and we'll come back and talk about it. The definition of linear velocity is the change in position with time. That means we're doing derivatives. So we need to do ddt of the quantity, position vector, from something to something, right? These position vectors, it's always some point with respect to another point. So what point is of interest? Point A. So if we take the derivative of the position vector in to A, what that is going to give us is it's going to give us the velocity of A with respect to N. Now N is a non-moving inertial point. So this A, really what we're saying is we're talking about the absolute velocity of point A with respect to that non-moving point. Consider, we could take ddt of position vectors, something like, what about A to B, right? This position vector doesn't start at N, so what would this give us? This would give us the relative velocity between 2 points. This would be the velocity of B with respect to point A, but recognize that point A itself could be moving. We're going to do more difficult problems where we have to do things like this. For now though, P into A, if the position vector is the absolute position, if it's starting at point N, oftentimes the syntax I will use, I will leave the N out. And then I would just write VA. So the implication then, if you see velocity of just a point, that's an absolute, and we've taken ddt of a full position vector. So you're often going to see me just write it this way. So we need to take ddt of this position vector. Now, position is a vector, that means velocity is a vector as well. So we can take, I erased it, but that's fine. We can take P in A, the definition of it, we said it was Q in the X hat N. All right. We're gonna take this very slowly so that everybody's on the same page. What I'm going to do with this ddt of Q X hat N is I'm actually going to expand this term. I'm gonna use a product rule expansion. And we're gonna write out all of these terms just so we can see them. So VA is equal to, if you recall, product rule expansion. Think about, example I always use is like ddt of X times Y. I think this is one people always remember from their calculus class. If you do ddt of X times Y, you get ddt of X times Y plus X times ddt of Y. Okay, so what does that mean for us right now expanding this? We're going to do ddt of Q multiplied by X hat N plus Q times ddt of X hat N. All right, so what does this mean? Well, Q is just a variable. Q is actually a scalar variable. And we use Q anytime there's a quantity in the product, in the problem that is changing. If it was a fixed distance, I wouldn't have used Q, I'd have used an L, right? So in this case, I know that Q changes. So what is ddt of Q? Well, it's literally ddt of Q, right? If Q is a position, then ddt of Q is speed. And what we're going to use is dot notation. So I'm going to write this as Q dot X hat N. And the dot literally means ddt. Next, what's going to happen on this part of the problem? Well, currently we're taking ddt of X hat N. And if you remember, the whole idea of the N frame is that it doesn't move. Just like the point N, frame N does not move, it doesn't rotate. So ddt of Xn, that means Xn is a constant, so ddt of Xn is 0. So this term, this is 0. So what is VA? What is the velocity of the block? It's just Q dot X hat N. And I'm sure many of you looked at this problem and you saw that within moments. How fast is the block going, right? What is the velocity at that point? Well, it's literally just this, Q dot. Okay, so this was an easy one. But this approach where we take the position vector and we expand it, when we're doing these at first, I am gonna show the product rule expansion a couple of times so that you can identify where these things go to 0. But it is going to get more complicated. So that's it for this one. Let me clean this up, and we're going to do the pendulum. Here's our pendulum, inertial point, inertial frame. We have some point at the tip of the pendulum, and we want, let's say we want omega into A, and we want VA, these two quantities. What do we need to add? Well, we know that we need to put a body attached frame, so XA and YA, and we know that we need some length because we're going to have to define this position vector. So let's just call that length L. Okay, by now we know the drill. Position vector, P into A, this is going to be L X hat A. Notice that I'm using the rotating body attached coordinate frame. Next, we need to define the rotation into A. We know how to do that. You do a diagram. There is a angle theta, and this is between the N frame and the A frame. So we have X hat A, this is cosine theta 1, Xn, sine theta 1 Yn. YA negative sine xn cosine yn, and it's a simple rotation about a shared z, so there we go. All right, all of this is in your notes. I expect you're comfortable with it by now. Let's move on. Next, how many generalized coordinates are there for this problem? I'm not going to write it down, but there's no translation in this problem. Understand, we know that point A is going to move, and if I put a point on the center of mass, that point would move too, right? They're all going to track the path of the circle. But in order to keep track of this body, in order to define the position orientation, we didn't need any translation variables. We can define it wholly with theta, so that means there's only one generalized coordinate in this problem, the angle theta, and it's independent, and you could freely spin this thing with your hand, so it's 1 degree of freedom. Okay. So what are we going to do about omega n to a? And remember, we had defined the rotation r into a, and this was a function of the angle theta. We can call it theta 1, that's fine. So the theta in this problem, theta 1, that's how we define this rotation. So what we're going to do with omega is we're just going to have the rate of change of this rotation, which is going to be theta dot. How does the angle theta change with time? Theta dot. And then, because this is a vector, we have to define how this body is rotating. And here's what I mean. I'm going to take my eraser and just consider this eraser could spin around this axis, it could spin around this axis, and it could spin around this axis. If this was an airplane, we would say roll and pitch and yaw. So it's not enough to just give me the scalar. You have to tell me what axis is it rotating about. So here's how we define the rotation, right? This thing is spinning around this axis. So what axis is that? That is the z axis. And you could say zn, you could say za. We know that they're the same thing. And that is how you write angular velocity. As I said, it's usually just from observation. You can look at the problem and you can address it. That is not necessarily true for all problems. We are going to do an example of a three-dimensional problem. And in that problem, we're going to have to use relative angles to kind of skip down the lengths. So this can get a little bit trickier in some cases. Also, if you're doing problems with general rotations, if this was a spacecraft and the spacecraft needs to do all kinds of spins, if it was a helicopter or a satellite or a commercial airplane, these get more complicated as well. Okay, next, linear velocity. So VA, I want the velocity of point A. What am I going to do? We're going to take the derivative of the position vector in to A. Now, when you're doing these problems, how much of these individual steps do you have to do? Not much. If you know what you're doing and you can dive right into the math, by all means do so. I'm going to take these little baby steps so that we're all on the same page. So we're going to take the position vector P into A, and let's drop it in here. It is L in X A, and we can do a product rule expansion on this term. We're going to have ddt of L multiplied by XA plus L ddt XA. All right, let's look at this. What happens here? Well, this length, L, is a constant. It's just some number. It's variable in the sense that we haven't specified it yet. This is a generalized pendulum. It could be a millimeter long. It could be 10 meters long. That still makes L a constant though, right? For that particular pendulum, the length L is constant. So this first term in the expansion, this term is 0. Next, L d dt of x hat a, okay? We know that x hat a is a direction. We know that it's a body attached direction. We know that when the pendulum moves, x hat a moves. So x hat a itself is moving, but what does it really mean to do d dt of x hat a? What we're going to do in these problems in this video, we're going to do it the long way, and I'm going to show you that this works. And then in another video after this one, you call it a trick. There is a theory that we're going to apply. It's called transport theorem. We're going to apply transport theorem moving forward in the class. But for today, I have to show you the long way so that you really understand what's happening in this process. So let's dig in to what that actually means. So VA is equal to ddt of, L ddt of x hat a. All right, what I'm going to do is I'm going to go back to our rotation that we did, our definition of rotation, and I'm going to take out what we said x hat a was, and I'm going to put it in. So this is L times ddt of cosine theta 1 x hat n sine theta 1 y hat n. I'm going to erase the stuff on top so we have somewhere to work. Okay. So here's where we are. We've taken, this is linear velocity. We're looking at a ddt of a moving frame. I have replaced this moving frame with its definition, and we're going back to the end frame. Quick comment, if you're using relative angles, and this were the D frame, then you'd have to roll this definition all the way back to the end frame. That's one of the reasons why relative angles can get more complicated, but just be aware that in the future we're going to be using transport theorem, and it's going to replace this long process anyway, which is really nice. So where do we go from here? At this point, recall that this ddt is a linear operator. What that means is I can distribute it to these two parts. I could rewrite this in this way. So let's put some brackets around this, and let's say now plus ddt sine theta 1 yn close, close. That's valid as well. At this point, what happens? Well, consider we could do a product rule expansion on these terms, and I'm gonna do that momentarily and then go back and erase it just to save space. But you could do a product rule expansion on this, and that's going to give you ddt of cosine theta multiplied by xn, and then cosine theta ddt of xn, right? Okay. So that's why I say when you're working these problems, recognize that product rule is going to come up often. You don't have to show each individual product rule. For example, looking at this product rule, I think we can just jump up there and say, okay, that thing's equal to 0. So you don't have to show each individual little step. It's fine. So what is this going to equal when we go through and resolve these ddt's? So what's going to happen is we're going to have an L out front, and we're going to take ddt of each one of these. And the first one, ddt of cosine, is negative sine. So negative, I'm going to write it like this. I'm going to say negative sine theta 1 x hat n. And then we're going to have plus ddt of sine is cosine y hat n. All right. You can see that I left a little bit of space in here because this is not quite it. We're not actually done. If this were the correct answer, then we should be able to say that VA is equal to this. And there's some magnitude here, and it has direction, so it's a vector that checks out. What are the units? In the way that I've written it right now, what are the units here? This is a length, and then this is sine of an angle. Well, sine of an angle and cosine of an angle, those are ratios. There's no units there. So if this is all you write down, then you're telling me that velocity has the units of meters, which makes no sense. We look at position vector, it would have the units of meters. Hey, that's fine. So something else has happened here. And clearly we're missing, if this is meters, and we know that the answer is meter per second, then somewhere in here we're missing a 1 over seconds, right? Okay, so what has happened, if you just go through and you take derivatives, right, and you say derivative of cosine is negative sine, you have forgotten chain rule. So, chain rule and product rule. These two, if you do not feel comfortable with these, I need you to go back and study these. Or at the very least, recognizing these problems when you need to use them. And practice them enough that you can do them correctly. So, we've been applying product rule, now we have to apply chain rule. And the chain rule crops up because we're not doing just derivatives, we're doing derivatives with respect to time. So you take the, you do the derivative with respect to time on the whole term, and then you go inside of the function and you take derivatives there as well. So what happens is we end up, I'm going to move the negative to the front, we end up with a theta 1 dot on both of these. There's our chain rule. And also that makes the units check out. This is meters, and the next one is radians per second squared. And when you multiply these, you lose the radians because the radian is just the connection to the arc length, and then you end up with meter per second. So that is going to be a linear velocity. We're not quite done with it yet though. We can clean this up a little bit. First of all, recognize that we can factor out the theta 1 dot. So VA equals, I'm going to say L theta 1 dot multiplied by negative sine theta 1 xn plus cosine yn. Okay. And in fact, we can simplify this again. What is this whole thing? If you go back and you look in your notes, you will see that that is actually, so L theta 1 dot y hat A. That's actually y hat A. So this whole process, what we did, we started with our original position vector. I'm just going to write it here. We had L xa. So there was the position vector. We wanted to take the derivative of it. We had to rotate this frame. We changed from the A frame to the N frame. We did our derivatives, and then we recognized that we can actually go back to the A frame. So I said we're going to do it the long way. This is the long way. And you can imagine having something like a robot where you have A frame, there's B frame, there's C frame, D frame, E frame. And we want to know what is the velocity of the end of the robot. Well, you're going to have to use relative angles on that robot, just because of the sensors at the joints. And then if you want to find the velocity, that means take E frame to D frame to C frame to B. I'm going to teach you a better way, different video. That's going to be transport theorem, and it allows you to take the derivative in these moving frames without ever having to go back to the base frame, to the end frame. We can actually take derivatives here in the moving frames themselves. Okay. So, let me, I erased it. I'm just going to rewrite it in a second. Before we move on to another problem, what I want to do is I want to go back to the diagram and I want to talk about that answer for just a moment. So let me redraw this. There we go. Okay. So, actually, tell you what, I'm just going to redraw the whole thing nice and big. And point A was out there. All right. So the frame that we put on this, XA was pointing this way and YA is pointing off like that. We had the position vector from N to A that was L in XA. We had VA as L theta dot YA. Okay. Let's look at these answers just visually. Let's see if they make sense. The distance from N to A is L in X hat A. I think we all agree there. But the velocity of A, the velocity of point A, is perpendicular. There's YA. We're saying that the velocity of point A is in that direction, VA. And later on, when this pendulum has spun, and point A is down here, there's XA, and that means VA is pointing off like that. So depending on the orientation of the A frame, right, depending on where the body is, the velocity is going to be rotating with that frame, and it's always going to be perpendicular to the path. It's always going to be pointing off the side. Recall, how does point A move? Point A moves in a circle. And the velocity of an object moving in a circle or some kind of curved path is tangent to that path. So the instantaneous velocity of A is always going to point tangent to the path of this circle, regardless of the orientation of this body. Now, what if it's rotating in the other direction? That means the numerical value of theta 1 dot will be negative, because it could be 5 radians a second, positive rotation. It could be negative 5 radians per second. It'll be a negative rotation, in which case you take the negative and just consider, okay, that means you're going in an opposite direction now. It's now negative. It's against y hat A. So if this were rotating in the other direction, the velocity of A would be pointing like that. So this checks out. This looks good. All right, let's, we got to do this third case now. And what I'm going to do is I'm just going to modify this, this nice big diagram of the pendulum that we have. And let's say that we cut a groove in this pendulum. So we put this thing on a mill and we slice out some space, and into this space we drop a block. So we're going to leave point A where it is, and let's put point B on this block. So the block itself, it's in the groove, and the groove is a part of the pendulum. So when the pendulum rotates, the groove rotates with it, and that's going to make the block groove. It's going to make the block rotate with the groove. We need an A-frame. We need a B-frame. And we need a distance. So this distance now is going to change. So there's a Q. Okay, what else? I erased point N, there's point N, okay. In frame. All right. So we've got all of that. What do we want? We want angular and linear velocity. So omega N to B. Now, how did we define our rotations? Let's say we did R in A, and we could do R in B. Recognize in this problem, we could also do relative angles. We could go from A to B, and that's possible as well. And depending on how we define these, this angular velocity definition might change just a little bit. But recognize really what's going on in this problem is that this block has to move with the A-frame. So a couple of things I could do. I could call out omega into A, and that's theta 1 dot z hat A. And then we could even say omega A to B is 0. And if I want omega into B, then that is the linear addition of omega into A and omega A to B. This is a nice thing about angular velocities is you can just add them together. So if you have that case of like a robot with all of these lengths, and they're all spinning and doing all kinds of stuff. A, B, C, so here's D. So if we want the total angular velocity from N to D, base frame all the way down to this wrist frame, then really we just have to find it for the individual parts. So N to A, and A to B, and B to C, and C to D. And you can linearly add all of these angular velocities together, and this will give you the total angular velocity vector for whatever that body is. And you'll get more comfortable with this as we go through, but just consider, it's kind of like saying this. I could take my arm, for example, and let's say we're just looking at two links. We're looking at my upper arm, my forearm, and consider that I could flip my elbow, and this would be like the second link. I could also rotate it at my shoulder, right? Or I could rotate both at the same time. I could rotate shoulder and elbow. And if I rotate shoulder and elbow, then the motion of my hand becomes a function of both of those rotations. So that's why we add these together. And this does also hold true even when you're operating in 3D, because you could have a spin around an x-axis and spin around a y-axis and spin around a z-axis. You could have all kinds of complex motion. Okay, so here's the claims for body B. You don't have to go through all of this detail. If you are capable of just saying omega into B equals omega into A equals theta 1 dot Z A, this is fine as well. All right, so somewhere in your problem, you give me some claim that conveys this information, however you need to construct it. All right, so next, linear velocity of point B. So what are we going to do? Well, we need ddt of the position vector, and that's going to be q in the x, and we could use xa or we could use xb. They are the same thing. So I'm going to use xb. And what's going to happen next? We're going to do a product rule expansion on this. VB equals, we will have ddt of q in the xb direction, and we will have q ddt of xb. Okay, we've actually seen both of these pieces addressed in the previous two problems. This was the piece that came out of the translation only problem, and this was the piece that came out of the rotation only problem. And you will notice that now when you have a body that is rotating and translating the block, it ends up being a linear addition of these two components. So what are we going to get for our answer? Well, we take this first piece, we take the derivative of just the scalar term, we end up with q dot xb plus. What's going to happen on this one? We're going to go back to our definition of rotation, just like we did in the last problem, and I'm going to replace that xb with cosine theta 1, sine theta 1. We're going to take derivatives of that. We're going to do product rule expansion if we need to. We're going to do chain rule. And eventually what you'll find is you can put it back in the B frame, and it's going to be YB. This process of chain ruling and product ruling, you always end up with, oh wait, I actually left something off. There we go. Chain rule, YB, okay. This process of taking these derivatives, you're always going to end up with similar looking terms, okay? You have some terms, hey little one. Some of these terms are going to be, you're going to have things like q dot. This is called slip velocity. The block is slipping in the groove. And then this next term, this is called tangential, because the velocity is tangent to the path. If we look at this diagram, we were able to do it for point A, right? We talked about what the velocity of point A looks like. We have an expression now for the velocity of point B. So what does this velocity look like? Well, you have a term in the xb direction. So the velocity of B, for example, it could look like this, and I'm going to say VB S, S for the slip. We have another term. Here is VB T for tangential. So you could potentially have both of these terms in the velocity of that block. Now, there's no guarantee that at a certain moment in time it's slipping, right? The block could be perfectly at rest. It could have no relative, there could be no relative change in this position vector. So Q dot at some instant could be 0. Similarly, maybe the pendulum isn't rotating at this moment in time, and theta dot is equal to 0. Maybe they're both equal to 0. Maybe there are cases where they both exist. Imagine a situation where the pendulum is rotating in a positive angle and the block has started from the outside and is working its way in. Depending on these numbers, right, and how fast they are to each other, you could have cases where it's like it's spiraling. If you were going to watch that happen, you would see that it's spiraled. Okay, so that's it for the problems. What I want to do is I want to clean this up, and I want to have one final discussion that's kind of what can we get out of this, and what's our intuition about velocity, because we are going to be moving forward into more complicated problems. Some final claims about velocity before we take off, and really this is about our perceptions of velocity. Imagine that you're in a car. It's a big family car. Mom and dad are up front, and in the back of the car you've got brother and you've got sister. And the brother is being kind of obnoxious, and he takes something, he wads up a piece of paper and he throws this projectile at his sister. Let's say that the car is going 60 miles an hour, and you, the observer, you're over here. You're watching it happen. So, from your perspective, what happens? First thing is you notice this car, and from your perspective, the car is going 60 miles an hour. You see it moving. Inside of the car, you see the brother hurl this projectile. And let's say, it's just like a playful toss or something, and he tosses it at 20 miles an hour. Now, maybe that seems really fast to you. Just consider that pitchers in baseball will chuck those balls at 100. Those are fastballs. So 20 miles an hour is it's just kind of a toss. From your perspective, though, if the brother is in line, the brother and sister are in line with the translation of the vehicle, that means from your perspective, you will perceive that this ball is traveling 80 miles an hour. So brother hits sister with a ball, and in classic sister fashion, she chucks this thing back at brother at 40 miles an hour. So from your perspective, the car is still going 60 miles an hour, and you perceive this ball as actually traveling 20 miles an hour in that direction. Even though she is throwing it to the left, the car is traveling to the right at a greater speed, and you perceive the overall motion of that ball in the direction to the right at only 20 miles an hour. We're going to back this up later when we look at relative velocities. We're going to do, for example, if you have a series of moving particles, and each one of these particles are moving inside of this inertial space, these particles, they perceive everything else as moving around it. In truth, in reality, we all perceive everything moving around us all of the time. It's only really with acceleration that we get any sensation of motion, or if there's drag, friction, something like that. You feel the wind blowing in your face, you feel like you're moving. But everything perceives all the rest of reality moving around it. So we all have this, if you're at a constant velocity, it's like you have, well, you do have a frame attached to you, right? If this is you, this is the U frame. When you were observing all of these objects moving with respect to your U frame, your own personal frame. Okay, so I feel like we all understand that intuitively. Let's do one more, and this is going to connect to that pendulum with the block in it. I want you to imagine that there is a disc, and there's a person standing in the middle of the disc. There's another person out here on the side, and they're observing, they're watching the whole thing happen. And then on this disc is a cat, okay? And that cat is staring at this person in the middle. So let's say this is you in the middle now. You're in the middle of this disc, and there's a cat just looking like right at you, giving you the dead eyes. And this disc starts to spin. If you're in the very center of this disc, you can imagine, the merry-go-rounds and things like that you've ridden on in the past. If you're in the middle of this spinning disc, then you're not going anywhere, okay? You'll have an angular velocity. You will physically be turning in place. But if you're exactly in the middle of the disc, you're not going to have any linear velocity. And the reasoning there, we could back that up with math. That's like taking that pendulum problem that we worked, and we had point A on the outside. What if we moved point A in? What if we put it right here? What if we put it here? We put it here, and every time we move it, we get it just a little bit closer to the joint that you're rotating around. Recall that the definition we had of linear velocity, in this case, it was L theta dot y hat A. So what we're doing is we're reducing the value of L all the way down to 0. When L becomes 0, then this is 0, and you have no linear velocity. So from your perspective, if that was you, you would observe the world spinning around you. Now you might get a little nauseous, right? Motion sickness, something like that. And of course your guts would be feeling the acceleration, but as far as the math goes, right? If you're perfectly here in the middle, you don't have any linear velocity. You perceive the world rotating around you, but you don't, we have difficulty perceiving the motion of our own frames, right? Because the frame rotates with us. Your friend, however, is looking at you spinning round and round all day long, because your friend is the in frame, and then you are this rotating body frame. So your friend sees you spinning, your friend notices that you don't have any linear velocity. That's okay. What happens when your friend looks at the cat? The cat is on the outside of the disc, and the disc is going to spin. And in a moment, the cat's going to be over here. And notice that when the cat has flipped to the other side, it's also rotated. It's rotated with the disc. The cat is no longer facing to the left, because the cat had its frame, and that frame is spinning. So what does your friend see? Well, your friend sees the cat, and it sees the cat turn, right, because it's on this rotating disc. And it also sees the cat have a trajectory around the outside of the disc. It observes this cat traveling in a circle. So it sees that the cat has a linear velocity as well. Final example, final case. Let's say that while this disc is spinning and the cat is spinning around, let's say that the cat, like I said, it's looking at you. This cat starts to walk at you, right? And it's coming towards you, and it's gonna come and get a piece of you. What would happen to that cat? Well, in your perspective, you're looking at the cat. In your perspective, the cat is walking directly at you, because you're both on the rotating disc. You're both on this spinning frame. And this cat is he's making a beeline for you, right? Straight line. Your friend, however, observes the cat moving in a spiral. So, this is just intuition, and it's kind of the games that our head plays when we think about how things move. All of this we can back up with math. We go back and look at those problems, and we did. And all of this is going to be helpful when you start working out future problems, right? When you go back and you look at your math and you ask yourself, hey, does this make sense? Okay. So that's going to be it for this video. What we're going to do moving forward on this topic of velocity is I'm going to teach you something called transport theorem. Transport theorem is going to greatly speed up the rate at which we can take derivatives of position vectors. It's incredibly useful for doing velocity. It is even more useful when we get to acceleration because it saves you even more time. It is in fact applicable when you're doing angular acceleration even. And we're going to look at some cases where this actually gets used in all kinds of places. We're actually going to use transport theorem when we do some discussions on momentum as well. So I strongly encourage that you learn to use transport theorem. I will not require that you use it. So on an exam or homework, you saw the long version today. You can do the long version if you really want to, and I'm not going to take points off for it, but you're shooting yourself in the foot and you're going to regret it later. Sorry. What else do we have to do? This is in no particular order. We have to look at velocity constraints as well. So we did all of the constraints. We have to talk about how the speeds are connected. And we actually dipped into that a little bit on the rolling and I think the pulley one. We talked a little bit about what happens to the speeds. I do want to make another video where we do a 3D problem. And the 3D problem is it's really going to show you how it becomes more complicated, more complex problems, more complex formulations. But I like doing this one because the approach is exactly the same. It doesn't matter if it's 2D or 3D. If you follow the recipe that I give you and you follow the formulations, you're going to be successful in these problems. And in order to do this 3D problem, this is a side thing, I am going to also make a video where we rotate about y and x-axis. So we've been up until now just rotating about z's. I need to give you the formulations for rotating about those other ones, and that'll help us do a 3D problem. And then there's going to be various other, one or two other things that I might dip into with this velocity. But we're going to spend about 2 weeks or so just talking about velocity problems. So make sure you're comfortable with what we covered in this video. And then the next real one, the next big one's going to be this transport theorem. Make sure you watch that video and you're comfortable as well. Okay, so that's it for this one. I'll see you around. Good luck.